Okay, last section in Module 7. And this section we're going to find the mean and standard deviation of the sampling distribution of a sample mean now. In 7.2 we were doing sample proportions, now we're going to do sample means. Calculate probabilities involving a sample mean when the population distribution is normal. So that's what we were doing on those last examples with normal CDFs. Explain how the shape of the sampling distribution of sample means is related to the shape of the population distribution, and apply the central limit theorem to help find probabilities involving a sample mean. All right. Sample proportions are from categorical variables. Okay. Sample means here, when we're dealing with means, they're going to be from quantitative variables. So that's the first thing you have to identify. Are we dealing with a proportion or are we dealing with a mean? Okay. So let's look here. Which of the following are proportions and which ones are means? U.S. adults that have watched Survivor, Guatemala. So U.S. adults who have watched Survivor, Guatemala. Number 2, adult population that attended church last week. 3, household income. 4, lifetime of car brake pads. And 5, blood pressure. All right, so number 1, if you watch Survivor, that's a yes or no answer. Yes, I watched it. No, I didn't. That's categorical, so it is going to be a proportion. We'll just write the symbol. Okay. Adult population that attended church last week. So you attended church or you didn't. That's categorical, so that's going to be a proportion. Household income, lifetime of car brakes, and blood pressure are all going to be the sample means. Okay? All right. Consider the mean household earnings for samples of size 100. Compare the population distribution, size 61,742 on the left with the sampling distribution on the right. What do you notice about the shape, center, and spread? Okay. The distribution of earned incomes is strongly skewed to the right and very spread out. The right tail of the distribution is even longer than the histogram shows because there are too few high incomes for their bars to be visible. So would you expect this? Yeah. So the distribution of sample means is roughly symmetric and much less spread out. Think of these 61,742 households as a population with a population mean of 69,750. Take an SRS of 100 households. The sample mean is 66,807. Take another SRS. Let's say that this one ends up being 70,820. So what would happen if we did this over and over and over? So graph B is a histogram of the mean earnings for 500 samples, each of size 100. The distribution of sample means is roughly symmetric and much less spread out. So when we're dealing with means here, we're just going to let the sampling distribution of X bar be the population mean. The standard deviation here is going to be sigma divided by radical n, as long as you have checked for that independence, that 10 times your sample is less than or equal to your population. Okay, so this is what we just said again. Sorry about that. Kind of have it repetitive. But no, the mean is just going to be the population mean, and the standard deviation of the sample will be the population standard deviation divided by the square root of n, as long as you can show independence. You can't do that standard deviation unless you show the independence. All right, so here you can just kind of see what's going on. Remember that the standard deviation is at that inflection point. So 1 standard deviation away is at the inflection point. Just another visual. Okay, so let's look at this one. Sulfur compounds such as, oh my gosh, DMS, are sometimes present in wine. DMS causes off odors in wine. So winemakers want to know the odor threshold, the lowest concentration of DMS that the human nose can detect. Extensive studies have found that the DMS odor threshold of adults follows roughly a normal distribution with a mean of 25 micrograms per liter and a standard deviation of 7 micrograms per liter. Suppose we take an SRS of 10 adults and determine the mean odor for the threshold X of the individuals in the sample. All right, so what's the mean of the sampling distribution? Well, that's just the mean of this mu going on of the population, which is 25. And what's the standard deviation of the sampling distribution? Well, as long as I can check that the 10% condition is met, then we can apply the formula. So let's first check that. 10 times our sample, which our sample was 10. So that is 100, which is less than all adults. So we're good to go there. So let's find out what our population standard deviation will be. So we're going to take our old standard deviation and divide by the square root of our n, and that's approximately 2.2. That was 10. Okay. Whew, that is really hard to see. I don't know why that looks so bad, but I'll read it for you. All right. We have described the mean and standard deviation of the sampling distribution of the sample mean x bar, but not its shape. That's because the shape of the distribution x bar depends upon the shape of the sampling population, unless, okay, which we're going to learn, unless something else happens. In one important case, there is a simple relationship between the two distributions. If the population distribution is normal, then so is the sampling distribution. This is true no matter what the sampling size. Okay, so young women's height. The height of young women follows a normal distribution with mean of 64.5 inches and standard deviation of 2.5. So find the probability that a randomly selected woman is taller than 66.5. Sorry. Is taller than 66.5 inches. All right. You could do the old Z formula. Or you could do this normal CDF. So here, if I wanted to do the Z formula and to find that if I had my mean and standard deviation of the density curve of 64.5 and the standard deviation of 2.5, then I could go and find that probability to be 0.2119. So what if I went and did it with the normal CDF? Since the population is normal, the sampling distribution can follow a normal distribution as well. So we could find the sampling mean, the sampling standard deviation, and if you wanted to do the z's, you could. Okay. So here it's going to be very unlikely that a 1% chance we would choose an SRS of 10 young women whose averages exceeds the 66.5. Okay. You could also do the normal CDF here. Okay. Here's just what the shapes would look like. Let's try this one. A grinding machine in an auto parts plant prepares axles with a target diameter of a mean of 40.125 millimeters. The machine has some variability, so the standard deviation is 0.002 millimeters. The machine operator inspects a random sample of 4 axles each hour for quality control purposes and records the sample mean of that diameter. Next part. All right. So assume that the process is working properly. What are the mean and the standard deviation of the sampling distribution? Well, my sample mean is just going to be the population mean. And my standard deviation is going to be, what was it, 0.002 divided by the square root of however many we're taking, which is 4, and that's equal to 0.001. So, how many axles would you need to sample if you wanted the standard deviation of the sampling distribution of X bar to be 0.0005 millimeters? So I want to know how many would I have to sample if I want that variation to be less than, to be equal to, it's usually less than or equal to, so equal to 0.0005. So we can put that over 1, cross multiply, divide by your 0.005, and then square. So we would have to take 16 an hour, okay, to have a variance that low. Okay. Oh yeah, we're going to find some probabilities. So, the length of human pregnancies from conception to birth varies according to distribution that is approximately normal, with a mean of 266 days and a standard deviation of 16 days. Find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. We have to show our work. All right, so we had a mean of 266, and we want to find 270 on. So I can do a normal CDF 270 to infinity, the mean, and your standard deviation, and get 0.4013. It's about 40%. All right, so suppose we choose an SRS. So that's just like for the population, okay? Now let's say we choose an SRS of 6 pregnant women. So now we're doing a sample. X is going to be the mean pregnancy length of the sample. What's the mean of the sampling distribution of X? Well, it's just the same as what we had before, which is 266. Compute the standard deviation and make sure we check that we can find that. So 6 times 10 is 60, which is less than the population of pregnant women. So let's go find sigma set X bar. So that was the original sigma divided by the square root of what we're taking, which is 6, a sample size of 6. That's approximately 6.53. So find the probability that the mean pregnancy length for the woman in the sample now exceeds 270 days. So this was back up here. That was for the population. This is now for the sample. So we have to do a normal CDF of 270 to infinity of 266, comma, 6.53. And again, here we're going to be finding that 266 and the 270 on. So you could either draw a picture or describe what you're doing. And this is approximately 0.27. Okay. A car company has found that the lifetime of its disc brake pads varies from car to car according to a normal distribution with a mean of 55,000 miles and a standard deviation of 4,500 miles. The company installs a new brand of brake pads on an SRS of 8 cars. If the new brand has the same lifetime distribution as the previous brand, what is the sampling distribution of the mean lifetime? Actually, why don't you go ahead and see if you can get this one. So see if you can find that mean and the standard deviation for the sample. And then part B says the average life of the pads of these 8 cars turns out to be 51,800 miles. Find the probability that a sample mean lifetime of that many miles or less if the lifetime distribution is unchanged. What conclusions can you draw? So I got the mean to be the same, 55,000, and the standard deviation of the sample to be approximately 1,591 miles. So when I went and found that probability, I got 0.0222. That's a very low sample, like that's 2%, okay? So I don't think the company is telling the truth. Now, the central limit theorem, and this is a website if you want to open the PowerPoint notes and go to it, you can click on it. The most population distributions are not normal. Okay, so what's the shape of the sampling distribution of the sample means when the population distribution isn't normal? So think back, as we increased in size, it gets more and more normal. We said, well, how big does it have to be? How much do I have to have? Okay, and that's what the central limit theorem is. It's like if I get bigger and bigger and bigger, then I'm going to become more and more normal. Okay, so how big do you have to get? Well, like this says, how large a sample size n is needed for the sampling distribution to be close to normal depends on the shape of the population distribution. If it was strongly skewed right, you'd want to get more. But for purposes, we are always going to say that we have to have greater than or equal to 30 to be normal. Okay? And again, if you want to go check that applet out. Okay, so describe the shape of the sampling distributions as n increases. What do you notice? It becomes more and more normal. So that's your central limit theorem. So let's do this example together. Servicing air conditioner, sorry. Based on service records from the past year, the time and hours that a technician requires to complete preventative maintenance on an air conditioner follows the distribution that is strongly skewed right, and it's shown over here, and whose most likely outcomes are close to 0. The mean time is mu equals 1 hour, and the standard deviation is also 1 hour. Your company will service an SRS of 70 air conditioners. You have budgeted 1.1 hours per unit. Will this be enough? Good question. All right, so let's go find the mean, the sample mean. That's just 1. What about the sample standard deviation? Well, let's check and make sure our 10% rule is applied here. So 10 times, how many do we have? 70 is 700, and I think that the population, that there are definitely more air conditioners than this. So I think we're good to go. So here I can see, again, we're dealing with means. So I'm going to take my previous standard deviation divided by the square root of my n, and I get approximately 0.12. Okay, so will this be enough? We have the mean, the standard deviation. We're going to have to do a normal CDF to see. So before I can do a normal CDF, we have to check what is our n. It's 70, which is greater than or equal to 30, so we can use normal. So if you want to draw a picture, the mean is 1, and we are looking for 1.1 on. It's our standard deviation point. So that's about 1.12. So we're looking about that much on. So let's do a normal CDF. Let's see, from negative infinity to 1.1, because we do not want it to exceed 1.1. We want it to be 1.1 or less hours, basically. And then our mean was 1, and our standard deviation was 0.12. If you want to go out more decimals there, you can. But that is approximately 0.79767. So about 80% of the time, you'll have enough time to complete the work. So you might have some angry customers if their technicians aren't going to be able to come. You'd have to decide in your business if you feel that that is enough time. Okay? All right. The composite scores of individual students on the ACT College Entrance Examination in 2009 followed a normal distribution with a mean of 21.1 and a standard deviation of 5.1. What is the probability that a single student randomly chosen from all of those taking the test scores 23 or higher? Show your work. Then take an SRS of 50 students who took the test. What is the probability that the mean score X of these students is 23 or higher? Show your work. So let's see if you can get that one. You can pause while you're working on it. And here are the answers. For part A, you should have got 35.57%. For part B, let's see, I got about 0.43%. And make sure you've checked everything appropriately. All right. So just kind of a sample of, or a flow chart of what you could have here. So if you have categorical data, you're going to go to proportions. Quantitative data, you're going to have means. So if this is your population, so you have your population mean and your population standard deviation. Okay. For means, you're going to have your sampling mean is just mu. And for proportions, your sampling mean is p. So for standard deviation, again, you have to check your 10% rule. But this is your formula if you're dealing with means. And this is your formula if you're dealing with proportions. To check for normalcy, you're going to have to say for means that n is greater than or equal to 30. Or the population was normal to start with. Okay. And for proportions, you have to show that n times p and n times 1 minus p are both greater than or equal to 10. So you have at least 10 successes and 10 failures. So this is like really nice little summary, okay, between 7.2 and 7.3, because you're going to have to decide what to use when. And here's an AP problem for you. I'll let you see how you do. Now that you have all of this knowledge, you can pause me, and then I'm going to go ahead and go to the answer here. And if you have questions, you want to talk about it, just let me know. Hopefully you did okay now, though. They showed it was Z's here. If you don't show it with Z's, you're going to have to tell me what everything means in that normal CDF, okay? Or draw a picture. And that's like if you did it with a calculator back on that other one, which hopefully you probably did. It's a little bit easier. Okay, here's another AP question. You guys know I put lots of these AP questions on your quizzes and your tests, so you can pause and then go check and see how you did. Got a little bit of binomial there, as well as the normal CDFing there. Okay. And here's a summary. And if you need anything, let me know. Good luck on your test.